Rohini College of Engineering and Technology from Department of Civil Engineering. So in this subject our final year students for 7th semester, our subject title is CE 8703 Structural Design and Drawing. So I am Michael Devadurai, Assistant Professor. So today we have seen our topic is design a welded plate girder. So design for plate girder with thickened web. So example 1. So design a welded plate girder of 20 meter span to support a uniformly distributed load of 70 kN per meter over the span using the following data. Then yield stress of steel is 250 Newton per mm square. The top flange is laterally restrained. So design the cross-sectional details of the plate girder to conform to the specifications of IS 800-2007. So given data, so effective span of the girder is 20 meter. Then distributed live load is 75 kN per meter. Then yield stress of steel is 250 Newton per mm square. And step number 1, load on plate girder. Then load on girder is equal to 1.5 into 70 into 20. So 1.5 is the factor load, 70 is the live load. Then 2100 kilonewton. So assume self weight is equal to total load by 200. So is equal to 10 kilonewton per meter. So total factor load is equal to 70 plus 10 is equal to 80 kilonewton per meter. Then step number 2, bending moments and shear force. So bending moment formulas, we know that simple formula WL square by 8. We know that W and L square. So W is equal to 80 and L is the 20 meter span. So apply it directly and you got the answers. So answer is the 4000 kilonewton meter. Then VD is the shear force. So WL by 2. So W is the 80 and L is the 20. So apply the answer 800 kilonewton. Then step number 3, cross section of the girder. So IS 800-2007, the page number 63 and 64. So depth of plate girder is, if you know one formula, D is equal to root of mk divided by fy the whole power 0.33. So m is the bending moment and k is the finding of the value. So we have the separate formula for the k. So k is equal to d divided by tw is less than 200. Then d is equal to depth of web, tw is equal to thickness of web. So yield stress ratios. So epsilon is equal to 250 by fy. So fy is given in our question. So 250 by 250 is equal to 1. So k is equal to 200 into epsilon. So 200 into 1 is equal to k is equal to 200. Then apply all the values in our depth formula. So d is equal to root of 4000 into 10 power 6 into 200 divided by 250 the whole power 0.33. So is equal to 1500 mm. Then adopt overall depth and d is equal to 1500 mm. Then adopt overall depth for allowing for 40 mm flanges plates. So depth of the web is equal to d is equal to 1500 minus 80. So equal to 1420 mm. Then thickness of web. Then d by tw is equal to 200 epsilon. Then tw is equal to d by 200 into 1. So 1420 divided by 100 is equal to 71 mm. Then d by tw is equal to 67 epsilon. So tw is equal to d divided by 67. So we know that the tw. So we find out this tw is equal to 1420 divided by 67 is equal to 21.2 mm. This is the thickness of web value. So adopt 20 mm thick and do 1420 mm deep web. Then width of the flange. So width of the flange is equal to 0.2d to 0.3d. This is our condition. So we know the depth of this rep. So apply the d value. So width of flange is equal to 0.2d to 0.3d. So we know the d value. So d is equal to 1420 to 0.3 into 1420. We got the answer is the 288 to 426. So we can approximately take as the 350 mm. Then adopt width of the flange is 350 mm. So see the diagram, see the I section. So our depth is the 1500 mm, we marked it. Then with the top flange and bottom flange is the 40 mm, then that's also marked in our diagram. Then width of the flange is 350 mm, is also marked that. Then thickness of web plate is 20 mm. So all the values are marked in our I sections. Then check for plastic and compact section for the ratio. So h by tf is equal to 9.4 less than 9.4. So epsilon is equal to 1. So tf is equal to 40 mm. Then hf is equal to 350 mm. Then 350 by 40 is equal to 8.7. So the ratio is satisfied the plastic section. Then step number 4, moment carrying, moment capacity. So the moment capacity of the plate girder is, we know the formula. So in this formula is page number 53, IS 800 2007. So the moment formula is a formula, just a copy from that code book. So we know all the values, so apply it, then you got the answers. So next apply the values, you got the answer. So is the greater than that value, so hence this section is the safe section. Then step number 5, shear capacity. So IS 800 2007, page number 59. So all the formulas in our page code book, so copy from that simple. So all the values are, if you know that, then apply the values easily. So V is less than Vd, so design shear strength. So Vd is equal to Vn divided by gamma m0. So first find out the Vn. So Vn is equal to Vp, then Vp is equal to AF into AW divided by Fy. So get the answer, so apply the values, you got the some answers. Then apply the values, so you got the answers. Then next Vd is equal to Vp by gamma m0. So we know the Vp value 4099186 divided by 1.11. So is equal to 3726533 kilonewton. So it will be greater than 800. So hence this section is the safe section. The next step number 6, check for bearing stiffness. So it will be taken from our code book, page number 67, from IS 800 2007. So Fw is equal to B1 plus N2 divided into Tw into Fy divided by gamma m0. So now we need to find out the minimum stiffness bearing length. Is it B1? B1 is equal to Hf by 2, Bf by 2. So Bf is equal to 350 divided by 2. Then is equal to 175 mm. Then N2 is equal to 2.5 into 40. 40 is the flange thickness. So 2.5 is the condition of our in our code book. See that. Then N2 is equal to 1000 mm. So Fw is equal to, apply all the values. So B1 is equal to 175 mm, N2 is equal to 1000 mm, then 100 mm, then Tw is equal to 20, then Fy is equal to 250 by 1.11. You got the answer is 1250 into 10 power 3 kilonewton. It will be greater than 800 kilonewton, so hence this section is safe. So see the diagram, this is our end bearing stiffness diagram. So plate girder, so we mark as the 45 degree, then B1, then bearing plate, then stiffener length at the support. Okay, see the diagram, I hope if you can understood. Okay, thank you.